Hello class, these are the preview material for tomorrow's lecture. One of my goal for this preview material so that you prepare yourself for the pre-class quiz. I just wanted to remind you the number of questions in pre-class quiz is always going to be higher than number of question polls and post-class quiz. So it is very important you review this material before coming to the class. Let's now first thing I am going to do is review the material I gave you guys last week. We have been talking about the calculation of K. In case of calculation of K for constant IV infusion, we have discussed three methods. One is use of estimated K, use CSS versus C, plot, and also use ln CSS versus C. This equation directly when you have two equations. So we'll learn another method, use ln C, log concentration against time, if you have plasma data after you stop the infusion. So first method, if you remember, if we have plasma concentration time profile data, and from this time profile data you can calculate T half time to achieve CSS, and then from that data you can calculate K using this equation. Another method we have discussed in detail, you have number of data before CSS, for example this one, you have number of data after CSS. In that case you calculate CSS minus C and take log of this and plot log CSS against time, and this will give you a straight line, and slope of this equation will be your K. Another method we have discussed, assume you have only two data, one before CSS, another after CSS or at CSS. So in that case you directly use this equation. For example, in this example you have a sample at 12 hours, which is before steady state, and 72 hours. So you plot this data, you put this data in this equation here. In this case the 72 hour data was 99.4 microgram per milliliter, 72 hour data was this, and then at the time interval is 12, and then you just put plug those data into this equation. This will give you K, and from this K you can calculate T. So another method to calculate K for IV infusion, constant IV infusion, assume that you have two data or three data. One is the last, assume that you have terminated the infusion, you have stopped the infusion, the last time point was this, which is 72 hours terminated, and then after terminating the infusion you took two more samples. You have only this data, last time point data, and then after two time points after termination of the infusion. In that case you can use these data, concentration data, and plot against time. So time you could use two ways. One is this, use log concentration here, and you can use directly this post infusion time. Post infusion time, that means you can use 0, 12, 24, or you can use that initial constant time point. You can consider, instead of 0 to 24 you can put 72, 84, 96. So if you take initial time into consideration, you can plot the data. Either way, if you plot the data, the outcome is going to be the same. You will have same elimination rate constant. We will practice this problem tomorrow in the class. Now, as I have mentioned, loading dose for IV infusion, for long half-life drugs we may have to administer an IV bolus dose to achieve CSS immediately, and that dose is called loading dose, and I have mentioned this thing in last class. Here you see this is the equation we are going to use. Remember this equation. In tomorrow's class we will practice a number of problems using this equation. And another thing I want you to remember, that influence of the loading dose on CSS, how loading dose affect the magnitude of CSS. Only thing you have to remember, only the infusion rate, not the loading dose, affect the magnitude of the CSS. For this reason, because loading dose will eventually be eliminated, so that's why infusion rate controls the magnitude of the CSS. And the initial plasma concentration from the loading dose could be higher than the CSS. You see, in this case it is higher than the CSS. Here in this case lower than the CSS. The C0 from the loading dose does not necessarily have to be CSS. It could be higher or lower. This concept you have to remember. Then now I will go over some relationship between the different parameters, like how CSS is related to CL and CSS is related to R, and how CSS is related to volume of distribution. I have discussed this thing in the class, these issues in the class last week. This class. Today I will show you some simulation how it works. Here you see this is a plasma concentration time curve for constant IV infusion. If you see, we are administering a drug at a rate of 10 milligram per hour. If we increase, if you see that at 10 milligram, if we increase, what is going to happen? The infusion rate, CSS. You see here CSS goes up with the increase in the infusion rate. Here we'll see now my effect of clearance. This log clearance is like 5 liter per hour. Now if we increase the clearance, CSS is going to go down. Now check the influence of volume distribution. See here, our volume distribution in this case is 20 liter. If we increase the volume distribution to 56, you see there is an inverse relationship. Now we'll check the influence of loading dose. Here there is no loading dose. Loading dose is 0. If you always look into this, and then if you increase the loading dose, you will see that CSS will be achieved first. You see, it's at a short time point, but it does not influence the CSS much if you increase or decrease. So because infusion rate controls the CSS, not the loading dose. So now let's go back to some questions. First I want you to know these are some of the questions you will see in tomorrow's course. These are the methods to calculate K for constant IV infusion. We have learned about 3 methods. One is t-half, use t-half. Another is you plot log CSS minus C versus time. Another is that you use directly the equation log CSS minus C, and that equation, whatever, you go back to and check with the equation. And then another method is you do not have any pre-infusion data, pre-CSS data, you plot log concentration against time. Which method would you use to calculate K for IV infusion if you have two or more post-infusion data? This is the method you are going to use. What controls the magnitude of CSS? Magnitude of CSS, infusion rate or bolus dose? Bolus dose. Infusion rate controls the magnitude of CSS. Loading dose must be equal to CSS, true or false? Not necessary. It could be bigger or smaller than CSS. Identify the plasma concentration time profile. I will give you profiles like this. It may have different color. I will say which one has the highest infusion rate or which one has the lowest clearance. Things like this. I hope you watch this video, and I'm pretty sure it's going to help you in tomorrow's class. Thank you.